Hello students, today's class we are going to discuss some of the important questions. So take the question from chapter number 4, that is moving charges and magnetism. Derive an expression for derive an expression for the magnetic field. Derive an expression magnetic field at a point along the axis of circular current loop. Along the axis of circular current loop. So derive an expression for magnetic field at a point along the axis of a circular current loop. So many times this question got repeated. Okay. So I'll take one circular loop here. So I'll take one loop which carries current in the anti-clockwise direction. So I'll take one loop here which carries current in anti-clockwise direction. Okay. So I is the current and R is the radius of the loop kept in the plane over there. Okay, just to draw the diagram here. So here is the loop which carries current in the anti-clockwise direction. This is the center of the loop and radius of this loop is R, and this is the axis of the loop. Okay. So at this point I want to calculate magnetic field. I call that point as P at a distance x from the center of the loop. At a distance x from the center of the loop. Center I call it as O here. Okay. So this is the y-axis and this is the x-axis here. This is the y-axis. This is the y-axis and here comes the z-axis. Okay, so this is the z-axis. And this loop carries current in the anti-clockwise direction, which carry current in the anti-clockwise direction. So I'll take now two diametrically opposite current elements. So one piece is here. So that is dl vector here. And one more I'll take here, diametrical opposite, so one more in this direction. Okay. So this dl at a distance, r from the point P. So join one line here to here. The distance how much? R. This distance is R. Okay. So we start our derivation now. So we'll write a magnetic field at P. Magnetic field at P due to magnetic field at P due to current element dl is magnetic field at P due to current element dl is, that is dB equal to Biot-Savart law apply nu naught by 4 pi I dl sin and theta divided by r square. This is the Biot-Savart law. So magnetic field at this point due to this dl is nu naught by 4 pi ideal sine theta by r square. Now what is the value of theta here? Theta is the angle between dl vector and this r vector. That theta is how much here? That theta is 90 degree. So sine theta becomes how much? Sine and 90, which is equal to how much? 1. Therefore, this dB value will become dB equal to nu naught by 4 pi. dB equal to nu naught by 4 pi IDL divided by R square. IDL divided by R square is the formula. Nu naught by 4 pi IDL by R square. Now, what is the direction of that magnetic field? What is the direction of that magnetic field? I'll show in some other color. So, I'll show like this. Magnetic field in this direction. This is dB vector. Okay, now this R and this dB both are perpendicular to each other. This R and dB, they should be perpendicular to each other. So keep that in mind. This dB comes somewhere here. This dB and that R both are perpendicular to each other. Okay. Now this dB neither in the x-axis nor in the y-axis. So we have to resolve this one. So I'll take this angle here as theta. Okay, this is my x-axis here. So here is my x-axis. So this is my x-axis. We resolve this and this is my y-axis here. Okay. If we resolve this dB, here becomes what? dB sine theta. And this one is dB cos theta. This is dB cos theta. Okay. So that point will write here now. Resolve dB into its rectangular components. So below that I write here. Resolve dB into its rectangular components. Now what will happen? We already resolved dB into its rectangular component. This one already we resolved. Now this much we got, which one? This dl. Similarly, one more dl is here. If I find the magnetic field at point P, that will come in this direction here. That will come here, dB. If I resolve this here, this become dB cos theta and here become dB sin theta. But we are not doing that one. Instead of that, we'll write in sentence. Just erase this one, it's not required. So if I do that one, what happens now? Vertical components are going to get cancelled out. Horizontal components will add up. So I'll write here vertical components cancel out. Vertical components cancel out, and horizontal components add up because both are in the same direction. Therefore, they get add up. Therefore, resultant magnetic field. Therefore, resultant magnetic field. Therefore, resultant magnetic field, what we'll get now? So that is B equal to summation of dB cos theta. Therefore, resultant magnetic field will become summation of dB cos theta. Only x component we have to add. So therefore, we'll write here summation of dB cos theta. Now after that, we'll find what is the value of cos theta. Since I'll do that one, cos theta. What is that cos theta? Cos theta is equal to capital letter R divided by small letter r. Refer this diagram here. Okay. If this angle is here theta means this here becomes how much? 90 minus theta. Therefore, here becomes theta. Here becomes theta means here becomes theta. Correct? Because this becomes 90 minus theta. So here becomes theta. Okay. So this is the radius I had not mentioned. This radius is capital letter R. Radius of the loop. Now this capital letter R, small letter R, angle is theta. So cos theta is adjacent side. This capital letter R by small letter R. Adjacent side divided by hypotenuse. So capital letter R divided by small letter r. That is the value of cos theta. So I hope that part is clear here. Cos theta is equal to what? Capital letter R divided by small letter r. Adjacent side divided by the hypotenuse. Okay. So just I'll mention this as r. Anyways theta here and here also theta comes. This theta here is not required. Okay. So capital letter R by small letter r. So already wrote here. Therefore substitute now. So B is equal to summation of dB. dB value how much here? dB value is here. Nu naught by 4 pi ideal by r square and this cost the value. Nu naught by 4 pi ideal divided by r square into capital letter R divided by small letter r. So B is equal to nu naught by 4 pi I into r divided by r cube. Square is that becomes r cube. And this step is you can ignore because both above and this step both are same. This and this step both are same. So just I will apply sigma for this dl. Okay, so B is equal to what will happen now? Nu naught by 4 pi I into r divided by r cube. So sigma dl becomes how much here? Complete length of the loop. So complete length of this loop becomes how much? Circumference, which is equal to how much? 2 pi r. Complete length of the loop that becomes 2 pi r. Okay, so if I rearrange and write that one becomes nu naught by 4 pi 2 pi I into r square divided by r cube. Now what is this r? That we'll find here. Once again this step and this step both are same. You can reduce the steps here. You can skip this step. You can skip this step because above and this one same. This and this are same. You can skip this or this. Anyone you can skip. Because both are same steps here. Now you'll find what is that value of small letter r. So refer this diagram now. Small letter r relation is here. Small letter r square. Pythagoras theorem you apply. Capital letter r square plus x square equal to small letter r square. Correct? Capital letter r square plus x square equal to small letter r square. So I'll write here now since small letter r square equal to r square plus x square. That means r equal to r square plus x square to the power half. That means r cube will become what then? R square plus x square to the power how much? 3 by 2. R square plus x square to the power 3 by 2. Therefore, B is equal to nu naught by 4 pi 2 pi I r square divided by r square plus x square to the power 3 by 2. R square plus x square to the power 3 by 2. Nu naught by 4 pi 2 pi I r square divided by r square plus x square to the power 3 by 2. Along which axis? Along x axis. Because starting only mentioned vertical components cancel out, horizontal components add up. So therefore vector form if you want to write this one, so that becomes nu naught by 4 pi 2 pi I r square divided by r square plus x square to the power 3 by 2 I cap. Why I cap? Because along x axis. X axis means we can write it as I cap. Okay, we can go through this revision once again now. Quickly we'll go through once again entire steps. Okay, so resultant magnetic field comes along x axis. So here comes B vector. Along x axis becomes B vector. So just I'll rewrite this one now. So this one is dB cos theta, and resultant direction becomes here B vector. So derive an expression for magnetic field at a point along the axis of circular current loop. So we'll take one loop which carries current in the anti-clockwise direction. Radius is capital R. Let P be a point at distance x from center of the loop. Now this loop carries current anti-clockwise direction. We selected two diametrically opposite current elements dl, which is kept at distance small letter r from this point P. So what is the magnetic field at point P due to this current element dl? So that is dB equal mu naught by 4 pi ideal sine theta by r square. Okay, what is the value of theta? Theta is 90 degree. Theta is angle between this dl vector and this r vector actually. Sine 90. So become mu naught by 4 pi ideal by r square. So what direction of magnetic field? This dB in this way. So angle between this dB and r is 90 degree. Perpendicular both. So if I do it for this dl, I'll get one more field dB in this direction. Both values are same. Directions are opposite. Now this dB neither in the x-axis nor in the y-axis. So I'll take here angle as theta. So I'll resolve this one. Here become dB cos theta and here become dB sin theta. So dB cos theta along x-axis and dB sin theta along y-axis. Similarly, if I do this one here, I didn't draw that one. So the same way will come. Here become dB cos theta, y-axis become dB sin theta. So that only right here. Resolve dB into its rectangular components. Vertical components cancel out and horizontal components add up. Therefore, resultant magnetic field become B is equal to sigma dB cos theta. Sigma dB cos theta. Okay. So sigma dB value how much? Nu naught by 4 pi ideal by r square. Cos value is how much? From this diagram here become theta. Capital letter R divided by small letter r. Adjacent side divided by the hypotenuse. Okay. So substitute values here. Sigma applicable only for this dl. So sigma dl becomes how much? Sigma dl complete length of the loop that becomes 2 pi r and r into r become r square denominator r cube. And what is that r square? Capital R square plus x square. So small letter r is r square plus x square is about half. So r cube is r square plus x square is about 3 by 2. So B is equal to nu naught by 4 pi 2 pi I r square divided by r square plus x square is about 3 by 2 along x axis. If you want to write in same in vector form, you can like this I cap because x axis indicates I cap. Next for a coil of n turns, note, this is actually a note. Coil of n turns, so I can write B is equal to nu naught by 4 pi 2 pi 2 pi I 2 pi n r square divided by r square plus x square to the power 3 by 2. Nu naught by 4 pi 2 pi I n r square divided by r square plus x square to the power 3 by 2. 3 by 2 is the formula. So just magnetic field becomes n times the original value. Nu naught by 4 pi 2 pi I and r square divided by r square plus x square power 3 by 2 is the answer. Okay, so I hope this is clear here. Important derivation. So next I'll go for another important question of this chapter. This force per unit length between two long straight parallel conductors carrying current and hence define ampere. We'll discuss that question now. Take the question. Derive the expression. Derive an expression for the force per unit length. Derive an expression for force per unit length. Unit length between 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 two long straight between two long between two, just ignore this part. So I read the question now. Derive an expression for force per unit length, force per unit length between between two long straight two long straight parallel conductors carrying current and ends define ampere. And ends define ampere. Okay, so this is a question here. For the important question, this also. So there are two very important questions are this chapter. One is circular coil and one more is force per unit length between two long straight parallel conductors carrying current, and we have defined ampere. Okay, so we'll derive this one now. So I'll take now two long straight conductors. Okay. So we'll take now two long straight conductors which are kept parallel to each other. So first one is wire is here. Second one is here. Both are parallel. Little thicker I will draw. Okay. Same wires. Just extend those wires here. Okay. So both carry current. So little bit change. I'll change this one. I'll draw thicker wires just to identification. Nothing else. Okay. So first wire and second wire. Straight wires, so you can draw straight. First wire carries current how much here? IA. Second wire carries current how much? IB. Okay, first conductor name is A and second conductor we'll call it as B. So here also carries same current here. Flows here IA and IB. Infinite long. What is the distance between these two? That distance we'll call it as small letter d. Okay. So what is the magnetic field? So we'll start our derivation now. So briefly I'll write here now. So magnetic field on B, on second conductor B, due due to first conductor. Because first conductor carries current IA, that produces magnetic field on B because a parallel on the conductor B throughout remains same. So that magnetic field I'll write as BA equal to nu naught by 4 pi 2 times IA divided by how much here D. Nu naught by 4 pi 2 times IA by D. Okay. Now what is the direction of this magnetic field? For that we should apply right hand clasp rule or right hand thumb rule. So that direction will come somewhere here. Later we can discuss actually what the direction. So first we'll copy this one now. So this is BA. This is the direction of the magnetic field B. Now this wire actually infinite, but I take one small length of this wire. That length I'll take it as L. Small piece of the wire will take length how much here L. Okay. Now in this magnetic field, this wire is kept. Second wire is kept. Now second wire also carrying current, and we know the concept. A current carrying wire kept in the presence of magnetic field that experiences force. So we'll write here now force experienced by B in the presence of magnetic field BA. In the presence of magnetic field BA. So what we can write here now? FBA equal to BA, magnetic first one, into IB, L, length into sine theta. Here what is the value of theta comes? Theta becomes 90 degree. Theta is the angle between length and the magnetic field. This is a length and the magnetic field. Both are perpendicular. So substitute value FBA is equal to BA value nu naught by 4 pi 2 times IA by D into IB into L. Sin 90 value comes how much here? 1. So this is the force experienced by the second conductor, that is B, in the magnetic field of first one. So what the direction of that force now? Force experience will come somewhere here by applying Fleming's left hand rule. That is FBA vector. Is the direction of force experienced by this B in the presence of magnetic field of first one. Now this is the force experienced by second one. Now what is force experienced by the first one due to second? Same amount of force but in the opposite direction. So you're not going to derive it again. So just will write that one sentence. Now we'll write similarly, if FAB is the force, FAB is the force on A due to B. Force acting on A, force experienced by A due to the current flowing through B. And what is that formula? That we can write as FAB vector equal to minus of FBA vector. Now both the forces are equal in magnitude but opposite in directions here. So FAB equal to minus of FBA. Newton's third law concept. Therefore, what is the force per unit length now? Then both forces are same thing but only directions are opposite. Therefore, calculate now force per unit length. Therefore, force per unit length FBA equal to FBA divided by L. So this L you bring this side. So that value comes how much now? Nu naught by 4 pi 2 times IA by D into IB. This is called force per unit length. Why I speak of this one? Because length of the wire is going infinite. Nu naught by 4 pi 2 times IA IB divided by D. So we'll go to the derivation once again. So derive an expression for force per unit length between two long straight parallel conductors carrying current and hence define ampere. So these two wires we have taken which are infinite long. So if we want to draw the same diagram, I'll just draw it here for reference here, just to understand the concept here. So this one carrying current, which one? IA. Second one carrying current, IB. Okay. So because of this current, there is a magnetic field on the conductor B. For that, we should apply right hand clasp rule. So what direction the magnetic field? That magnetic field will go into the tape. That is going in. In means cross mark. That is into the screen. Right hand clasp will apply in. That is magnetic field B. Now in this magnetic field, the second current carrying conductor, this one is kept. So that experiences force. For that you should apply Fleming's left hand rule. So thumb point direction of force, forefinger point direction of magnetic field, and a middle finger point direction of the current. So where the current is going? Current is going above. Correct here. Magnetic field is inward. Where your thumb is going to point? Thumb will point like this. FBA. This is the direction of the force. That only shown in a diagram, but alignment is different. So this magnetic field is into the screen here in this diagram, and force comes towards the wire, first one here. Okay, the one more point is possible here that we'll discuss little later. Okay, so just go through this part now. Magnetic field on B, on this wire B, due to A is B equal mu naught by 4 pi 2 times Ia by D. Now force on B in the presence of magnetic field of first one, that is force experienced by second one, FBA equal to magnetic field of first one, current flow in second one into length into sine 90. So mu naught by 4 pi 2 times Ia IB L by D. So direction of force is shown here. Now similarly, if FAB is the force on A, FAB is the force on A due to the second one, in that both are going to experience same amount of force but in the opposite direction. Same amount of force but in the opposite directions. So we can write FAB equal to minus of FBA. Next we calculate force per unit length. Force divided by length. This length you bring here. So mu naught by 4 pi 2 times Ia IB divided by D. The one more question is pending there to answer. Ampere. That we define now. Okay. So ampere definition will write. So it will define 1 ampere. So don't write definition of ampere from the current chapter, not that definition. By taking reference of magnetic field, we should define ampere. So what is 1 ampere? You have to take the reference of this formula. Then we have to define what is 1 ampere. Okay. So how to define this one now? So in this one, what are variables are in this formula? Nu naught by 4 pi value we know, 10 to minus 7. 2 times Ia value how much 1, Ib value how much 1, distance how much 1. So this value comes how much? 2 10 over minus 7. What unit of force? Newton. What unit of length? Meter. So becomes Newton per meter. So this we are going to represent in our statement of 1 ampere. Okay, so just we'll write the statement now. 1 ampere definition. Okay, so 1 ampere 1 ampere. Okay, 1 ampere is that 1 ampere is that steady current. 1 ampere is the steady current which when flowing through each of two infinitely long straight long straight parallel conductors long straight parallel conductors of negligible cross section, negligible cross section placed 1 meter apart, 1 meter apart, 1 meter apart in a vacuum, 1 meter apart in vacuum, produces between them a force of 2 into 10 power minus 7 Newton per meter. 1 ampere is that steady current which when flowing through each of the two infinitely long straight parallel conductors of negligible cross section, the thin wires, placed 1 meter apart in vacuum, produces between them a force of 2 10 power minus 7 Newton per meter. Produces a force of 2 10 power minus 7 Newton per meter. This is the definition of 1 ampere. So 2 into Ia is 1 into Ib is 1 divided by distance is 1. So only remains this much constant, mu naught by 4 pi into 2. So the value become 2 10 power minus 7 Newton per meter. So this is a derivation of force per unit length. The one more note point you can take here. Please take the note point. Now multiple choice questions are there. So these questions can come. Now two wires going to carry current in the same direction. So what is the nature of force between these two? I repeat again. When two wires carry current in the same direction, here in this case you can see both the wires carry current in the same direction. In that case, what is the nature of the force? Here nature of the force is attractive. Here nature of the force is attractive. They are going to attract each other. Nature of the force is attractive here. When two wires carry current in the opposite direction, nature of the force is repulsive. When two wires carry current in the opposite direction, nature of the force is repulsive. When two conductors carry current in the opposite direction, nature of the force is repulsive. Opposite direction repulsive, same direction is attractive. Okay. Next, we'll go to next question now. So in this one more question is the conversion of galvanometer to voltmeter and galvanometer to ammeter. So we'll discuss these things now. Those are 3 marks possible questions. So take the question now. How do you convert? How do you convert? How do you convert galvanometer into ammeter? Into ammeter. Okay. So just brief explanation right here. So how to convert galvanometer to ammeter? What is ammeter? Is an instrument used to measure current flowing through that one, and it offers very low resistance. And ammeter always connect in series. Those things about ammeter qualities. Now, how do you convert galvanometer to ammeter? We'll write that one. A galvanometer is converted into an ammeter by connecting a low resistance by connecting a low resistance parallel with galvanometer. A galvanometer is converted into an ammeter by connecting a low resistance in parallel with galvanometer. By connecting a low resistance in parallel with the galvanometer. Okay. So first we'll draw the circuit diagram. This is one galvanometer. This is one galvanometer. So to convert galvanometer to ammeter, now I want to use the galvanometer to measure the current. How much here? I. Actually, I is the current flowing. I want to convert that one. Now this is actually I is the current flowing. Now what I'll do is I'll connect one small resistance in parallel with the galvanometer. Okay. That resistance is known as shunt resistance. Shunt resistance, yes. Okay. Now what happens here now? I is the current coming here. Now current splits here. So what is the current flowing here? This current I call it as Ig. So what is the current flowing here then? I minus Ig. So I is the current coming here. Splits. Here flows Ig and here flows I minus Ig. So once again now current becomes how much here? I. Once again becomes here I. So same thing we can redraw this one now. Whatever we did here conversion, then whatever inside this block, this one part will act as an ammeter. That much part will act as what? Ammeter. What in the dotted line I mentioned, that will act as ammeter. Okay. Now we derive equation for this one now. Potential difference across G, the galvanometer equal to potential difference across which one here? Yes. Potential difference across G is equal to potential difference across S, because these two are connected in parallel. So that is Ig into G equal to what? I minus Ig into what here? S. So S is equal to the formula Ig into G divided by I minus Ig is the formula. So required shunt resistance is S is equal to Ig into G divided by I minus Ig. Okay, this is the S value. Now just explain the terms here. So what is this Ig? Ig is the current. Okay. Ig is the current. Ig is the current produces full scale deflection in galvanometer. Ig is the current produces full scale deflection in galvanometer. Then what is this I? I is the range of the ammeter. I is the range of ammeter and G is resistance of the galvanometer. G is the resistance of the galvanometer. And what is this S? S is the shunt resistance. S is the shunt resistance. S is the shunt resistance. Okay. These are just term explanation and it's a formula. Could be a 3 marks or 2 marks on numerical may come. Possibilities. How do you convert galvanometer into ammeter? By connecting low resistance in parallel with galvanometer. So here Ig, I is the current entering on small resistance connected in parallel with the galvanometer. So current splits here. So here Ig and here flows I minus Ig. So remaining current once again I. So whatever dotted region that we call it as ammeter. So potential difference across G equal to potential difference across S. So Ig into G equal to I minus Ig into S. So S is equal to Ig into G divided by I minus Ig. Ig is the current produces full scale deflection in the galvanometer. I is the range of the ammeter. G is the resistance to the galvanometer. And S is the shunt resistance. Next, one more note point for ideal ammeter. For ideal ammeter, what is the effective resistance or internal resistance we can say? Effective resistance of the ideal ammeter is equal to 0 ohm. So internal resistance of an ideal ammeter is 0. Internal resistance of an ideal ammeter is 0. Okay, so these many things about conversion of galvanometer into an ammeter. Okay, so next we'll discuss about conversion of galvanometer into a voltmeter. So next we'll discuss about conversion of galvanometer into a voltmeter. So next question. How do you convert galvanometer into voltmeter? How do you convert galvanometer into voltmeter? Okay, so solve this one now. So how to convert galvanometer to voltmeter? First point, how we are going to connect voltmeter in the circuit. Voltmeter connected in parallel in the circuit and voltmeter offers very high resistance. So what about galvanometer? Galvanometer offers very low resistance in comparison with the voltmeter. So in order to convert galvanometer to voltmeter, we should connect some high resistance in series with the galvanometer. We have to connect some high resistance in series with the galvanometer. So right here now, a galvanometer is converted into voltmeter by connecting a high resistance a high resistance in series with the galvanometer. A galvanometer is converted into voltmeter by connecting a high resistance in series to the galvanometer. Why you have to connect high resistance series? Because galvanometer offers very low resistance in comparison with the voltmeter. So in order to increase the resistance to the galvanometer, we are going to connect high resistance in series. Okay. So we'll draw the circuit diagram here. Some current is flowing the circuit here. Here is the galvanometer. Okay, so this is the galvanometer and this is the high resistance in series, and we want to measure the voltage here V. So I is the current flowing and here is the current Ig. Now this much portion is called as a voltmeter. Okay. Now same thing we can replace what is circled region and replace it as a voltmeter. Okay. So we'll write here now V is equal to what is this one? This voltage Ig into R plus G. So R plus G is equal to V by Ig. R plus G is equal to V by Ig. So R equal to the formula then V by Ig minus G. Okay. Now what is this Ig? We'll explain the terms. Ig. Ig is the current. Okay. Ig is the current. I is the current that produces full scale deflection in a galvanometer. Next, G, resistance of the galvanometer. G, resistance of the galvanometer. What is V? Range of the voltmeter. V, range of the voltmeter. R, resistance connected in. Resistance, sorry, R is the high resistance connected in series to the galvanometer. R is the high resistance connected in series with the galvanometer. High resistance connected in series with the galvanometer. Okay, so these many things about conversion of galvanometer to voltmeter. So question was, how do you convert galvanometer into voltmeter? A galvanometer converted into voltmeter by connecting high resistance in series with the galvanometer. So galvanometer is high resistance in series and that volt is written as V. Ig is the current flow in the galvanometer. So V is equal to Ig into R plus G. So R plus G is V by Ig. So R equal to V by Ig minus G. Ig is the current that produces full scale deflection galvanometer. G is the resistance of galvanometer. V is the range of the voltmeter. R high resistance connected in series to the galvanometer. Next we'll write for ideal voltmeter. Ideal voltmeter. Effective resistance is or internal resistance of an ideal voltmeter is infinity. That means we should increase the resistance of the galvanometer by connecting high resistance in series. So what is the maximum value you can connect? Maximum we can connect infinite resistance in series. Infinite resistance in series. In this way you can convert galvanometer into ideal voltmeter by connecting infinite resistance, or that voltmeter should offer infinite resistance. Infinite resistance. Okay. So today's class we discussed about magnetic field along the axis of the circular loop, force per unit length, and conversion of galvanometer voltmeter concept. So these four questions we discussed. And two wires carry current in the same direction. Nature of the force is attractive. When two wires carry current in the opposite direction, nature of the force is repulsive. Then here some other important questions are possible. You can go through those. In the later classes, we can revise those theory type questions. One is state Ampere's circular law. State Ampere's circular law and derive an expression for magnetic field due to infinite long straight current carrying wire. That could be one 2 marks or 3 mark question. You can go through that one. Obtain an expression for magnetic field due to straight current carrying wire. And other questions are possible is one. What is solenoid? What is solenoid? And write the expression for magnetic field due to a solenoid or toroid. Both equations are same. That is B is equal to nu naught N into I. B is equal to nu naught N into I is a formula. This formula. B is equal to nu naught magnet due to solenoid or toroid. Nu naught we know. Absolute permeability of free space. And N is number of turns per unit length. And I is the current. And B is the magnetic field. And one more question is torque experienced by the loop or rectangular loop in the presence of magnetic field. The one more is cyclotron. Cyclotron. Those that is easier. You can go through by yourself. Theoretical question that one. And some other questions is one. When the charge is moving perpendicular to the magnetic field like this, charge is moving perpendicular. And path traced is circular. When theta is 0, path traced is straight line. When theta is neither 0 nor perpendicular, in between comes and path comes helical. So these are the questions comes under this moving charge and magnetism. So I hope these many things are clear over here. So what are things we discussed over here? So these are the remaining small concepts you can go through if time remains, and the later classes we are going to discuss those things or you are going to revise it once again. And the next chapter there are no much derivation, magnetism and matter chapter. So important questions are properties of diamagnetic, paramagnetic and ferromagnetic material and Gauss law in magnetism. Then properties of magnetic field lines. Then comes some definitions. Hysteresis, retentivity, coercivity and Curie's law. Like this some definitions are there. You can go through those. Okay, so I hope all these points are clear here. So I'll stop here now. So next class we can discuss some other questions. Okay, I'll stop here now. Thank you.